Okay, so the point that we were at yesterday was we had just begun to find the area of the region bounded by the limacon. So a couple things, we remember that a limacon looks like A plus or minus B cosine theta, or A plus or minus B sine theta. So we got that much together. And then we were trying to find the area inside this, and they told us we went from 0 to 2 pi. So a couple of things I usually like to check is a few points. So here, when theta is 0, r is equal to 3 plus 2, which is 5. So this would be the 0.50. And then we are doing the cosine, so it's marching around the curve. And we say theta equals pi over 2. R is equal to R is equal to 3 plus 2 times 0. So that's 3. So this is the 0.50, and this is the 0.03. And then when R theta equals pi, R is equal to 3 plus, and the cosine, 2 times the cosine would be minus 2. So that would be 1. So this is the 0.10 minus, minus 10. So you're going in the direction of pi 1 unit. So that's minus 10. So that lets me know that that's half. So that's why I could tell you that yesterday. Okay, so now we have, this is 1/2. This should be r squared. All right, so now we get the 2 times the 1/2 drop out. So I get 1, 0 to pi. And inside, I'm going to get 9 plus 12 cosine theta plus 4 cosine squared theta, d theta. And we have to remember that cosine squared theta is equal to 1/2 times 1 plus the cosine of 2 theta. So we are going to take this and plug that right in here. So when that 4 multiplies by that 1/2, we're just going to get a 2. All right. So therefore, we end up with the integral between 0 and pi of 9 plus 12 cosine theta. And then we're going to get 2 times 1 plus cosine 2 theta. Theta. So now we're going to integrate this. And let's simplify one more time. Integral between 0 and pi. So I'm going to take the 9 and 2 and give me 11 plus 12 cosine theta plus 2 cosine 2 theta, d theta. So now I'm all ready to do my integration. This becomes 11 theta plus 12 sine theta. And then this becomes the sine of 2 theta. Evaluate between 0 and pi. And when you put everything in, you just end up with 11 pi. And that's it. Okay. Okay. So here's another area problem. Find the area bounded by each loop of the limacon with equation R is equal to 1 plus 2 cosine theta. And that's all we give you. Okay. All right. So a couple things I can do with this one is anytime I can look to see first off where it starts and see if there's a place where the R becomes 0. Because I'm still trying, I have to graph this thing so I get an idea of what it looks like. So the first thing I always do is what is theta equals 0? R is equal to 1 plus 2. So it equals 3. Okay, so let's start this thing off by knowing it's at the point 1, 2, 3. Now, this other limacon, I could have done the same thing and tried to see if there was a place where the limacon became 0, and I would have found out that there's not. So since there's no place the limacon actually goes back to 0, that let me know that it doesn't come back in. Whereas this one actually does. So if I set it equal to 0, I get R equal to 1 plus 2 cosine theta. And set that equal to 0, I find out that the cosine of theta is equal to -1/2. And there are 2 places where it goes back to 0. So that the places are, that's theta is equal to 2 pi over 3 and 4 pi over 3. So between those points, if I just were to do a line here, so here's 0, and here's 2 pi. And at 2 pi over 3, and 4 pi over 3, in those exact places, the radius is exactly equal to 0. Okay, so that means it's crossing over the origin at those points. But another thing that I can find out from this is that if I look and put in a theta between 0 and 2 pi over 3, so let's choose theta equal to maybe pi over 2. So if I choose theta equal to pi over 2, I get R is equal to 1 plus 2 times the cosine of pi over 2, which is 1. So I see R is positive here. So this is R. So R is positive there. If I put in pi, I get R is equal to 1 plus 2 times cosine of pi, which is negative. So R is negative, and then here is positive. So now this is what it lets me see. It lets me see that I can even put in and see what happens at theta equals pi over 2. So let me just do a couple. So over here, this is what I know so far. At theta equals 0, R is equal to 3. At theta equals pi over 2, R is equal to 1. And at theta equal, R becomes 0 when theta is 2 pi over 3. So you can see R is shrinking and then it shrinks down to 0. Okay, so let's graph these thetas for a moment. So here is theta being 2 pi over 3. And then here is theta being 4 pi over 3. Okay. So I know that here I get the point 0. Oh, yeah. R is 3. I know that when I get the pi over 2, R is 1. And then I know when I get to this angle, I go back to 0, so I'm here. So I already know my thing looks like this, because it's coming back in. I already know that. But then the thing that's cool is I also know that between at theta equal to pi, r is -1. So this thing has to come all the way back around to, now this is pi, so pi is in this direction, but r is -1, so it goes in the opposite direction. And so now I've graphed 1/2 of this thing. And the way it keeps going is it goes like this, and then this comes back out here, and then this comes back around, and it goes back around like that. So that's what this limacon looks like. All right, so it says, what's the area bounded by each loop of the limacon? Okay, so if I do the integral, if I just do the area from 0 to 2 pi over 3, that is going to give me the whole entire shaded region. Okay, so that's just going to give me the top part, the whole shaded region. What in the world? I have no idea what just happened. There we go. I don't know what that was. Okay, so I know that I'll get the outer part of the loop is, so the whole upper half. So I'm gonna, before I mess this up, I'm gonna draw it again. So let me lasso this. Okay, because I need that again. Okay, so if I do the integral from 0 to 2 pi over 3, it's going to give me all of this. It's going to go down here, and it's going to give me all of this area in here. Just like that. So I'm gonna get that. So that part, so this piece is the integral from 0 to 2 pi over 3 of 1/2 r squared gives me, it's 1 plus 2 cosine theta squared d theta. Okay, so that is going to give me that whole piece. Now, if I do the integral between 0 and 2 pi, between 2 pi over 3 and pi over 3, I'm going to get the whole inside of this. Okay, so this piece is the integral between 2 pi over 3 and if I only, so, and I do integral between 2 pi over 3 to 4 pi over 3 of 1/2 of 1 plus 2 cosine of theta squared d theta, I'm going to get that whole thing. So technically, what I really want is I want this piece that's inside that loop, and then the outer loop is this piece. So what I'm going to do is I'm going to do the first one and then multiply it by 2. And then I'm going to do 1/2 of this one. Where am I? Oh, and then that'll give me the whole middle piece. So, okay. So let's do the first piece. All right, so the first piece, so the area, in order to get that first piece, we're going to call that A1, is the outside. So that area A1 is 2 times the integral from 0 to 2 pi over 3 of 1/2 times 1 plus 2 times the cosine of theta squared d theta. And I'm going to integrate this just the same way I integrated the other one. So this becomes the integral between 0 and 2 pi over 3. And then I'm going to get 1 plus 4 cosine of theta plus 4 cosine squared of theta d theta. Are you with me, Anaya?
Yes.
Okay. All right. So then this becomes the integral from 0 to 2 pi over 3 of 1 plus I have 4 cosine of theta plus 4, and then I'm going to multiply by 1/2 times 1 plus the cosine of 2 theta, just like we did before, d theta. So now I get the integral from 0 to 2 pi over theta. I have 1 from here, and I'm going to get 2 from over here. So that's going to give me 3 plus 4 cosine theta plus 2 the cosine of 2 theta d theta. And then this integrates to 3 theta plus 4 sine theta plus sine of 2 theta evaluated between 0 and 2 pi over 3. So I'm going to get 3 times 2 pi over 3 plus 4 times the sine of 2 pi over 3 plus the sine of 4 pi over 3. And when I'm done, that turns out to be 2 pi plus 3/2 the square root of 3. Okay, so that's what I get when I simplify that. Okay, so that's the pink region, the total pink region. And so now I need to do the inner loop part. So that's A2. So A2 is the integral between 2 pi over 3 and 4 pi over 3 of 1 plus 2 cosine of theta squared d theta. Okay, I already know what that's going to integrate to. We did the integral. I'm missing a 1/2. So we did the integral. So we already know that when you do the integral, you get 3 theta plus 4 sine theta plus the sine of 2 theta. But this time we're evaluating it between 2 pi over 3 and 4 pi over 3. And when you stick that in, you end up with pi minus 3/2 the root of 3. So therefore, the area bounded by those loops is the third picture. So that's the area bounded by the loops is just the purple part. I should have maybe did it a different color. Yeah. Okay, that's what we wanted. There we go. All right, so if you take the whole purplish region minus the green region, you get what we're trying to solve. Okay, so therefore the bounded area is A1 minus A2. And that means you take 2 pi plus 3/2 square root of 3, and you subtract pi minus 3/2 square root of 3, and you end up with pi plus 3 to square root of 3. Okay. Now you can find the region bounded between two different curves. So say you have two different curves. R1 equal to F1 of theta, and R2 equal to F2 of theta. And you wish to find the area of the region between the two curves. Okay. Well, that's the area of the region. So I have something that looks like this. And then maybe I have something that looks like this. And I want to find the region between the two. So maybe I want, so R sweeps out like this now. So R goes like this. It starts at the origin and it goes out from R1 to R2. And I want to sweep out this region. Okay. Well, if you notice the area and it, so here, I'm going to start from this theta. So I'm technically going to start from this theta right here. And I'm going to go up to this theta right here. And R is going to sweep out the region between the two. So now I know that 0 is less than or equal to R1 of theta, which is less than or equal to R2 of theta. All right. And alpha is less than or equal to theta is less than or equal to beta. All right. So I have two things. So then the area between the two, the integral from alpha to beta of 1/2 R2 squared d theta minus the integral from alpha to beta of 1/2 of R1 squared d theta. And that becomes the integral from alpha to beta of 1/2 of R2 squared minus R1 squared d theta. So here's an example. Find the area A of the region that lies within the limacon R equal to 1 plus 2 cosine theta, and outside the circle R equals 2. Okay. So we have something that looks like this. So actually, let's go back and take that Lima sign that we had before. Good, it still remembers it. Okay, so here is my Lima sign. R equals 2, and then I need a circle of radius 3. I'm sorry, a circle of radius 2. So now I need a circle of radius 2. So let's see. That's just about right. So there's the circle of radius 2. Let's move it over. Okay. So we want the area that's inside the Lima sign, but outside the circle. So we want this area right here. Okay. So we have to find out our theta that they intersect. Okay, because the theta where it intersects is, it intersects, the theta where it intersects is right here. And then the other one is right there. So theta is going to start at, so this angle down here is alpha, and the angle up top is beta. So this angle, we got to figure out, this is alpha, and this angle is beta. So we got to figure out those. And then any R sweeps between the two. Okay. All right, so let's set them equal. So we get 1 plus 2 cosine theta has to equal 2, or 2 cosine theta has to equal 1, or the cosine of theta is a half. So that says theta is equal to negative pi over 3 and pi over 3. So we're going from down there to down there. Now, the other thing we could recognize is it's symmetric. So we really don't have to go from minus pi over 3 to pi over 3. We could just do 2 times the integral from 0 to pi. So the area of the region we want is 2 times the integral from 0 to pi over 3. Of 1/2. Now I'm going to need R2 squared minus R1 squared d theta. So the 2 and the 1/2 are going to go away. So I'm going to get 0 to pi over 3. R1 squared, R2 squared. Well, R2 is the furthest one. So R2 is actually the 1 plus 2 cosine of theta squared. And then the R1 is simply the 2 squared. D theta. So this then becomes the integral between 0 and pi over 3. Here I'm going to get 1 squared plus 4 cosine theta plus 4 cosine squared theta. And then I'm going to subtract off 4. And we're going to do what we did before And that ends up simplifying to the integral between 0 and pi over 3. I'm going to end up with 4 cosine theta. This piece becomes 2 cosine 2 theta. And I'm going to end up with 1 minus 3, which is going to give me negative 4 plus 1. So I get negative, nope, this should be in, yeah, that should be a negative 1. Yes. Okay. Integrate that. So I'm going to get 4 sine theta plus sine 2 theta minus theta. Evaluate between 0 and pi over 3. And that comes out to be a little cray-cray, 5/2 square root of 3 minus pi over 3. It's not cute, but that's the answer. Okay. All right, so that's how you do area problems. So do you have any questions? Inaya?
Okay.
Yes.
So
Yeah,
everybody's good with that? So we'll
Yeah.
say our first name and then our school.
I'm sorry.
Okay.
Yes, what'd you say?
Do you have any questions?
No, as of right now, I'm just following everything you're going through.
Okay.
I always look at the recordings anyway. If I would have questions, I usually ask. I'll probably ask tomorrow.
Okay, that's good. Okay,
Yeah, because sometimes I don't really understand until I relook at it.
I understand. Yep. Okay. So let's talk about the length of a curve. Okay, so the length of a polar curve. Okay, so this is not as bad as one would think. It's actually develops, the theory develops very nicely. Again, we have to remember what we had before. Okay, so the parameterized, so the length of a parameterized curve is L is equal to the integral from alpha to beta of the square root of x prime of t squared plus y prime of t squared dt. So with the polar curve, we parameterize it slightly different. Okay, so r is equal to some function of theta. X is r cosine theta, which makes it f of theta cosine of theta. And y is r sine theta, which makes it f of theta sine of theta. So now I need to compute dx d theta. And so that's f prime of theta times cosine theta plus f of theta times negative sine of theta. And dy d theta, or y prime, is equal to f prime of theta times the sine of theta plus f of theta times the cosine of theta. So now dy dx d theta squared becomes f prime of theta squared cosine squared theta minus 2 times f prime of f of theta, f prime of theta, sine theta, cosine theta, plus f of theta squared times sine squared of theta. And dy d theta squared turns out to be f prime of theta squared times sine squared theta plus 2 f of theta, f prime of theta, sine of theta, cosine of theta, plus f of theta squared, sine squared, cosine squared theta. Okay. So now if you add these together, on the left-hand side, you're going to get x prime of theta squared plus y prime of theta squared. I'm going to have f prime of theta cosine squared of theta plus f prime of theta sine squared of theta. I can factor out cosine and sine and just get f prime of theta squared. These two are going to divide out, we'll add, subtract out, okay? And then the last two are going to give me f of theta squared times sine squared and cosine. So I'm going to get f of theta squared. And I can conveniently write this as r squared plus the derivative of r with respect to theta squared. So therefore, my length now comes the integral from alpha to beta. I have square root, and then I'm going to have r squared plus dr d theta squared d theta. All righty. So here's an example. I like this example too. Find the arc length of the spiral r is equal to e to the theta. 0 less than or equal to theta less than or equal to pi. Okay, so clearly as theta gets bigger, r gets bigger. So this is a spiral. When theta is 0, it starts off at 1. And then it just keeps getting bigger. And that's from 0 to pi. So we want to find that arc length. Okay. So r is e to the theta, and dr is e to the theta. So r squared is e to the theta squared, but that's just e to the 2 theta. And dr d theta squared is also e to the 2 theta. So r squared plus dr d theta squared is e to the 2 theta plus e to the 2 theta. But that's just 2e to the 2 theta. Okay. So therefore the length, the integral from 0 to pi, square root of 2e to the 2 theta, d theta. But now I'm going to get the square root of 2, that's going to come out. And the square root of e to the 2 theta is just e to the theta. So that's the integral between 0 and pi of e to the theta d theta. So I get the square root of 2. And then I get e to the theta because I integrate between 0 and pi. So I get the square root of 2, e to the pi minus e to the 0, which is 1. And there's my answer. Nice, fun problem. Okay. I think we're going to end up doing at least another example. Let me scroll up real quick. So they only want you to know arc length of a polar curve and the formula for the area. I don't think we're doing surface area of revolution. I will check. If not, I'll just do another arc length problem, and then we'll be ready to move on to conic sections.